It's going to be just like the way we're going to do it today. Okay, her question was, what is the test going to be like? It's going to be basically very similar to what we're doing today. You're going to have some balancing equations, and don't forget there's the extra credit balancing equation as well. Okay, go ahead and look at that if you've not already done it, or files, files test related. It's short but hard. Now I'm toying with the idea of having a, usually I have a take-home question as well for test 4. So look for that very soon. Yeah, I'll send you a message that it's posted and where it's posted. Minor details, right? Okay. And this topic we're going to talk about today, you're going to cover in the first week and a half of 1A. Maybe the first 2 weeks, depending on who you have. And they're going to expect that you've had this before. So it's really important. I'm going to give you a whole week to really digest this. And there is tons of practice. If you go to files, unit 4, or if you go to modules, unit 4, you'll see a zipped file with lots of practice. And I'm talking about like 20 worksheets or so with answers and setup. I just want to bombard you with lots and lots of opportunities to practice. Okay, so I want to review a problem with one given. And we did a bunch of these a couple weeks before the break. Okay, so how many grams of water are produced from burning 12 grams of methane, CH4? Okay, so first thing you need to do is I will give you the balanced equation, which is right up here. The balanced equation, it'll be unbalanced on the. Okay, so her question was, am I going to give you the equation? Yes. However, when you get to 1A, you will not be given the equation necessarily, depending on who you have. So based on the verbiage there, you should be able to write that equation. Okay, but I'm going to give you that equation in Chem A. Okay. Step number 1, as always, is balance it. Okay, so given is 12 grams of methane. And the first step always is to take the given and convert it to moles. Okay, so carbon is 12.01 and hydrogen is 101, and there are 4 of them. So that's 1605 total. Now, what we're trying to calculate is how many grams of water. So we want to end up with grams of water. Okay, from the balanced equation, we get the ratio of the coefficients from the balanced equation of what we were trying to calculate and also what's given. So notice our CH4s cancel, our grams cancel. Now we want to take moles of water, which we have now, to grams of water. Water is oxygen is 16 grams, and we have two waters at 101 apiece. So that's the setup. So we're looking at 26.9 grams of water. Now, that's with one given. Now, hopefully you all were able to follow me on this because we're going to be multiplying this by 3 if there are 2 givens, and by 5 if there are 3 givens. No, just 2. 2's enough. All right. Does anyone have any questions about this? This needs to be clear, clear, clear. No mud needs to be entered into this thought process. All right, we start with the given. First thing we do with the given is convert it to moles. Next thing we need to do, we're going to do the mole ratio from the balanced equation, which is the ratio of the coefficients. Given's on the bottom, so it cancels. And the next thing we need to do is convert the moles of what we're trying to calculate into what we're trying to calculate. In this case, grams, but it could be gaseous liters. It could be a number of atoms or molecules. Okay. So for the test, I'm expecting you to know these 3 conversion factors. Avogadro's number, 6.02 times 10 to the 23rd, 22.4 liters per mole for any gas, and then the molar mass from the periodic table. Those 3 you need to be comfortable with on this test. Now, we have 4 steps for problems. We have balance the equation, what's given, what are we trying to calculate, and what's the setup using conversion factors. Now, if we have 2 givens, this is modified then. Now we modify the setup here, okay? Still got to balance the equation. Still got to figure out what's given. What's to be calculated, just like before, only this time we have to figure out which of the givens limits the reaction. So let me give you one that I've already mentioned before, but just as a review. Okay, we have 20 wheels. This is a bicycle thing again. We had 20 wheels, one given, 4 frames, second given. How many bicycles can we make? 4. Why not more than 4? 4 frames limits the number of bicycles. So the number of frames is the limiting reactant because it limits the number of what you're trying to calculate or product. In this case, it's the bicycles. We don't have enough frames to go around, to use up all the wheels. So we're going to have excess wheels left over. How many wheels are going to have left over? 20 wheels. We made 4 bicycles, right? Each one's 2 wheels. That's 8 wheels. So we subtract from what's given. So our 12 wheels in excess. So there's 2 parts to this problem. Frequently 3, but 2 parts for the one I just mentioned. One, what limits the reactants? How much product do we get? Which one is going to limit it? Frames or wheels? And how many bicycles do we make? 2 parts. Frequently, the third part is how much excess of the reactant do we have left over? In this case, 12 wheels. And sometimes there's a yield thrown in there too, how efficient we are, okay? All right, so normally on all my problems, you're gonna have to do 3 parts. You have to figure out which limits the reaction, how much product you produce, and lastly, how much excess do you have left over of the one that you don't use up. Okay, so bless you. 12.3 grams of methane is burned in 15 grams of oxygen gas. So right away, you're going, this is getting more complicated. So we have 2 givens here. We have our good old methane being burned, and we need to balance it real quickly. So which limits the reaction? The oxygen gas or the methane? And we have to do a calculation to determine that. Now, calculation is going to look very familiar. And I ask you how much excess is left over. Then I also tell you, if 2 grams of water is produced, what's the percent yield? Okay, so step number 1 is to do each given like it was by itself. So we're going to take 3 grams of methane, and we want to go to water. Right now, we're ignoring the oxygen. And we're going to do a similar calculation, ignoring the methane, using only oxygen. Because now the product is water. We want to see which one produces the least amount of product. Okay, the least amount. So to grind it out, first step is always convert to moles. And that was then we do the ratio from the balanced equation. And then okay, so that's just like what we've been doing. We're ignoring the other given. We need to grind it out. Okay, so that's 27.6 grams of water. If we ignore the oxygen gas, that's step number one. Step number two is we need to do the same deal, only using oxygen. Oxygen is 16 grams per mole. There are two of them, so that's 32. Okay, so if we start with 15 grams of oxygen, ignoring the methane, we're going to produce only 845 grams of water. We do the reciprocal calculation, methane ignoring the oxygen, we get 27.6. So which limits the reaction, the oxygen gas or the methane? Oxygen. It produces the least amount of product. We don't have enough oxygen to go around with all the methane we have. Just like with the bicycle, we don't have enough frames to go with all the wheels. Okay, so that means for this problem, we're going to make 8.45 grams of water, no more. Now, the second part of that is how much excess is left over. So we have we have excess methane now we have to deal with. How much excess do we have? Well, the first thing we need to do is figure out how much we used. Well, we're going to start with oxygen again. And this time our product is going to be how much methane was used up. So we're going to end up over here with grams of methane. Okay, so based on 15 grams of oxygen, how much methane are we going to use? That's what this calculation will tell us. Bless you. So we're only going to use 3.76 grams of methane. But we had a whole bunch of methane. So how much do we have left over? So the last calculation okay, we started with of the 12.3 we've used 376. So that means we have an excess of 8.54 grams of methane. That's what was given. Remember, there were two givens. I had a methane and an oxygen gas. Okay, so you can see that the reason why I wanted you to work through these practice problems over break is that these were exactly one given problems, but there are three of them. And you need to combine them all together to figure out, one, how much product we're going to get. We got 8.45 grams of water. That's product. That's first part of the question. The second part is how much excess of the non-limiting reactant do we have? And that's this calculation here coupled with this subtraction. Yeah. When we have first two equations, figure out which limits the product. We don't know that. You can't tell by looking at it. You have to actually do the calculations. Right. Yeah, but what if we had tons of it? Like I have a match. Let's play like the match is methane burning. Okay, and I have this room full of oxygen, which is going to limit the amount of carbon dioxide I make. The match or the room full of oxygen? The match. Right. Not the oxygen. Okay, and then there's one little tidbit left over. I said if 2 grams of water is produced, what's the yield? That's just a simple percent calculation. So we made 845 grams of water. Theoretically, the theoretical part comes from the calculations, not the actual lab. Now today's and tomorrow's lab is called stoichiometry, lab 11. And you're going to take baking soda and drop in acid till it stops reacting. And then you're going to measure how much carbon dioxide, you're going to measure how much is left over by drying it and weighing it. And that would be the actual yield. So the actual yield in this problem is 2 grams of water. Theoretically, we made 3.76. Theoretically, not actual. So the percent yield is equal to actual over theoretical times 100. So in our case, it's going to be 2 So 53.2% yield. So actual is what we actually weigh when we're all done with doing our little experiment. Theoretical is from the calculations. And that's one problem. What about, I'm sorry? No, just see how well things went. Whenever you do a reaction, it never is perfect. Never. And the purpose, one of the purposes of a chemical engineer is to take a process and you want to maximize yield. So looking about, for example, my first job out of graduate school was with Spreckels Sugar. My job was to maximize the yield of sugar production. So what we did is we went and looked for all kinds of stuff like leaks and stuff, how proficient our crystallization was, all this stuff. So I was acting like a chemical engineer, where they did look at the process, design it to maximize yield, but it's never going to be 100%. In fact, who's heard of molasses? Okay, that's what's left over after you crystallize the sugar, is molasses. That nice dark stuff, got a lot of flavor, got a little dirt in it usually. The sugar beets come into the factory, they are muddy, banged up, bruised sugar beet roots. And when it leaves the factory, you have this nice crystalline white powder. In between is a lot of muddy water and sloshing around and all kinds of stuff. It's amazing how much, and that's one way of purifying also is crystallization. All right. Okay, so let me do another problem for you again. And so before I do that, are there any questions about this? So we've got, have to do two reactions right off the bat. Boom. Which is giving us the least amount of product. You start with each given acting independently. And then I tell you the product. I said how much of whatever is produced. That would be what you calculate towards. Yeah. Actual is what we did in the lab. I said, okay, we did this. We ended up weighing how much water we made, 2 grams. Okay. However, if we'd have been super duper, really, conscientious and did all the right stuff, we should have gotten 3.76 grams. We only got 2. So theoretically, we couldn't get any more than 376 though. That's the maximum limit. Okay. Now I've got a bunch of these practice problems for you. As I was saying earlier. In fact, let me just show you where they're all located. This zipped file, that will be where they're all located, and the files are going to Files, Unit 4, and these are all the worksheets available. Besides the ones in your dry labs. They've been here for, which one should you be practicing? Well, these are all, I give you the answers in all these, but the setup and everything. Yeah, all of my worksheets have the blank problems and then another set with the given the answers. Yeah. For example, okay, and then here are all the answers. And the limiting reagent ones. So here's the blank, and then there's the setup. Was that your? Well, there's a lot of them here. Which one? This one here. That's one we just looked at. It'll say limiting reactant or limiting reagent if it's a multi-step one like we did today. If it doesn't say that, it's a single one. In lab, we can go over this more. You have lab today, right? Okay. So as you can see, there's a lot of worksheets here. Equation balancing. Tomorrow, we're going to talk about empirical formulas. By the way, I have to change a grade. Who sent me the email about their grade? Oh, well, okay. All right. This is a real life problem. In your body, your body needs to make energy. The energy is in the form of adenosine triphosphate, ATP, and that's made in the mitochondria inside your cells. So we are going to take glucose. Now, a lot of foods are converted to glucose and fructose because they're macromolecules, whatever. But the mitochondria need glucose. They can burn fructose as well. They need glucose though. Okay, so if we have 34.9 grams of glucose and 14 grams of oxygen gas, how much carbon dioxide is produced? So one of the reasons we have lungs is to get oxygen to the cells so they can undergo glucose combustion. And the reason why we have lungs is to get rid of the carbon dioxide produced, which is not good for our body. Okay, so first thing is, you need to know the formula for glucose. Now, all carbohydrates have this ratio. Carbohydrates are made up of carbon, hydrogen, oxygen. And the ratio is for monosaccharides. Okay, so it's twice as much hydrogen as carbon and oxygen. So how many hydrogens do we have? If we have a 6-carbon hexose, 2 times 6 is 12. So that's the formula for glucose. Now, obviously, on a question, on a test, I would give you the molecular formula for glucose. Now, fructose has the same formula, maltose, all the monosaccharides have the same formula. In fact, in workout journals, you'll frequently see carbs referred to as CHOs. That's the ratio of the hydrogens to carbon. Oh, there's just an N. It could be an X or, So say we had sucrose is a disaccharide with a glucose and a fructose in it. Okay. So we have two givens. We have oxygen gas, we have glucose. So it's going to be a limiting reactant problem. So let's start with oxygen gas this time. Okay. The next step is from the equation, which is going to be so step number one is balance the equation. So is it balanced as written? No, far from it. So we have what? 12, 18. Yeah, it's balanced now. Okay. So oxygen is 6. And carbon dioxide is also 6. And carbon dioxide is molar mass is 1201 for carbon, 2 oxygen, that's 32. So we're looking at 4401. And that'll give us grams of carbon dioxide. Okay. So right now, looking at the oxygen by itself, we're going to get 19.3 grams of carbon dioxide. Now this headset of mine is giving me a low battery. So towards the end of this video, my audio is going to trail off. All right, now we need to use glucose to start with, okay? So we have 34 grams of glucose. Okay, so we have okay. Just the oxygen gas. In this case, the oxygen gas limits production of carbon dioxide. Because it's small. How much excess will there be? It requires another calculation. We're going to use the limiting reagent this time, which is the oxygen. And we're going to end up with seeing how much of the carbon of the glucose is used up. Okay, so this will tell us we used up all the oxygen, all 14 grams of the oxygen. How much of the glucose was used up? And then the rest will be excess. So if we use up all the oxygen, 15 grams, we're only going to use 13 grams of glucose. So we started with 4.9. So how much excess do we have? Now, that number 15, at number 19.3, is that theoretical or? I'm just saying. They say 9 grams. Okay. Why not now? You try one on your own. Okay, so 2 givens, 34 liters at STP of oxygen gas, 12.3 grams of methane are burned. How much water is produced? How much excess will there be? And what's the yield if only 1.23 grams of water is produced? Now, this is a full-blown problem. 2 givens. We're going to be looking at number of reactions, reaction calculation. So go ahead and try that. And you're going to be using 22.4 liters per mole. This one, not the molar mass of oxygen gas. Because you need to convert the 34 liters of oxygen gas per mole. First step, so 22.4 per mole. There's the balanced equation. Again, why? This is part of the Class. We all have the content. I hope they went through from singer, program. I won't be consulted.
Well, okay. I have like 5%. Sunday, I think so, you know what I'm saying, like, I need to go, depending on how far I'm going, I want to do that one, and I mean, like. That's. Hi. Well, okay with that. Okay. So, but, I saw the rules. He didn't do whatever.
Look at this,